811 polyatomic ions, formal charge. Wow. Okay. So AP students, yes, suddenly time shift. You saw me there in the past. The other lessons, I had the old chalkboard. What I showed you in the first video on polyatomic ions is good. It's good. It's a way to write, it's a theory to write the Lewis dot diagram for polyatomic ions that would work for probably for some of them. It will give you some information correct. But to get more of them correct, I want to go over something else, something called formal charge. This is an important concept that's on AP, and it is not something that I show in my general class. So the first video you saw was general, even honors. I think I showed it in honors, but I can't find the video. Maybe I didn't make a video, and maybe I just taught them live, or I don't know what I did. But anyway, here's the deal. There are some times that the octet rule can be broken by some polyatomic ions, by certain ones. I'm going to say a little bit more about that in a later video you'll get. But anyway, here's the deal. Let me start off with iodate, which I did in the video you saw before. If I say write the Lewis dot diagram for iodate, I'll explain it in this way. All right. So first, I've talked about using the ABC method. You go in there, and first of all, you calculate the number of electrons. Iodine has 7 valence electrons. There's one iodine atom times 7 valence. If you already saw this in the first video, you can scrub past it if you want to, if you don't want to see it again. Oxygen, but I'm going to show you something different here. I'm going to show you something different, so watch. Oxygen, there are 3, each has 6 valence electrons. And then you have a -1 charge, which means you have to have one more electron. I'll put plus. So that will be 26 total electron dots in the picture. Now, if you do the ABC method, or the A28BC, A28BC, so 2 times the number of hydrogen atoms, and there are 0 hydrogen atoms in this one, so that's not going to matter. I don't know a good way to really write this down. 8 times all the others, so there's 1, 2, 3, 4 atoms. 8 times 4 electrons, or I'm sorry, no. 8 electrons times 4 is 32. B is the number of valence, which is 26. So 32 minus 26 gives you 6 bonding electrons. Now, this is what we did in the first video. And so then we said, let's decide which atom will go in the middle for IO3. And here's my chart there. And iodine and oxygen. So you think, well, who is a more metallic element? Well, you normally would say, well, what is it? Is down or over? What is it going to be? We'll also go by Funkelbrich, okay? Remember that in Funkelbrich, the most electronegative is fluorine. So hydrogen will be the least electronegative in that set and the most metallic. So more metallic will be this way. Okay, so iodine, obviously, more than oxygen. So, and plus, because it looks right, because I mentioned that, I think, in the video. Iodine, and we'll put 3 O's around it, and we'll say, okay, I'm going to give it 6 bonding electrons. So there has to be at least a single bond, and a single, and a single, and when I do that, I've already got my bonds, at least I think, okay? And then what you do is make sure everyone has 8 electrons around it. So 2, 4, 6, add 2 more for iodine. 2, 4, 6, 8 has access to 8 electrons. Oxygen 2, 4, 6, 8 access. 2, 4, 6, 8 access, and 2, 4, 6, and 8 access to 8 electrons. Then you would also need to make sure you put brackets around it and put the charge on the outside, -1. Okay, so for our general class, that's all I require, but not for AP, not for college. Let me show you why. Remember this. This whole method I've showed you, the little ABC method and the octet rule, the official method, octet rule, all this is just something that scientists like Lewis put together to try to explain what we see happening in chemistry with molecules. That does not mean that everything has to follow those rules. Well, it turns out that a lot of polyatomic ions break the rules when it comes. A lot of them break these rules, and this is not really what it's like. In other words, when they do an analysis, like a spectral analysis to analyze molecules of iodate, they find that it does not have 3 single bonds. Okay, and like we see here, 3 IO bonds and a lone pair. Instead, they find something different, and what happens is we're going to apply a concept called formal charge based on Lewis dot based on formal charge. Now, first, let me show you formal charge. There's a couple of ways you can write the equation for that, and I don't even know which one your textbook uses, but this is what I used to. I'll show you what I always heard before. The formal charge of an atom. Now, formal charge is just it's not the ionic charge, but it's the charge of an atom in a covalent molecule. A charge given to help this better describe bonding or the type of molecule you'll have, whether it's single or double or triple or whatever, and who's bonded to who. Formal charge is equal to the number of valence electrons that an atom has minus the number of electrons it claims. Or, all right, that's the easy way to remember it. For oxygen, this oxygen, this iodine, each of those 4 atoms have a formal charge. To find it, I'm going to take the number of valence electrons of the atom, and I'm going to subtract the number that atom claims, the number of electrons that atom will claim. Now, another way to say is number of valence minus the bonding electrons. No, the number of all lone pair electrons and minus half the bonding. Oh no, half the bonding electrons. Now, this is the formula that I go by. This is a formula that makes it a little bit more detailed. And then there's even another formula that I just saw. I'm going to show you, I'm going to write them all down. They all give you the same number. It's just another way to word it. So, formal charge is equal to the number of valence electrons for an atom minus the number of electron it claims. Or the number of valence electrons for an atom minus the number of lone pair electrons it has minus half the bonding electrons. I'll explain this in a minute. And then the other way, this is one that I use with the UCLA program. It's the number of valence electrons again. So you start with the valence minus the number of non-bonding electrons minus the non-bonding. That's the same as lone pair. Minus the number of bonds. How about that? They work it that way. Valence electrons minus non-bonding minus number of bonds. Or valence minus the number of lone pair minus half the bonding. Or valence minus the number of electrons it claims. Okay, what in the world is all this I'm talking about? Well, here we go. So, let's just start with an atom. In fact, let me write it up here so that I can do it above it. We can look at all 3 of them. Let's look at the atom of oxygen. Well, actually, let's look at this oxygen first on the left. It turns out all 3 of these are kind of identical. So they're going to all have the same formal charge. Sometimes they don't, but on this molecule they do. This oxygen right here, the number of valence electrons for oxygen is, look on the chart, it has 6 valence. 1, 2, 3, 4, 5, 6. Remember I told you about that? 7, 8, all the way across. So 6 valence electrons minus the number of electrons it claims. Well, here's a simple rule. An atom in a molecule can claim, for formal charge, an atom can claim all the lone pair. Lone pair only belong to that atom. Okay? They're not shared. So these only are like part of the core, or what you might want to say for, well, I'll say part of the core, even though they might be in the valence area, but they can't be shared. So 1, 2, 3, 4, 5, 6. You have it can claim 1, 2, 3, 4, 5, 6 lone pair, and it can claim half of the bonding electrons, half of the shared ones. So 1, 2, 3, 4, 5, 6, and then there's 2 more, but it can only have half. So half of 2 is 1. 1, 2, 3, 4, 5, 6, 7. 6 minus 7 equals negative 1 is the formal charge of this oxygen molecule. I'm sorry, oxygen atom in the molecule. And let me erase this so it doesn't look like a big mess. It's a negative. It's really hard to write this on your paper because you almost want to have another color, like a pen or a different color with you, just so you don't run into all the pencil and all that. Maybe a blue pen would be good to write it, or a red would be even better, I guess. Negative 1 charge. Okay. Now, if you want me to, I'll just show you why this works also. The number of valence in oxygen is still, all oxygens have 6 valence, minus the number of lone pair, 1, 2, 3, 4, 5, 6. Okay, so 6 minus 6, and then minus half the bonding electrons. Well, I just told you that. That was part of my little rule too. You have 1 bond, so half of that would be 1. So it would be minus 1 more. So 6 minus 6 minus 1 equals negative 1. See, it still works. Or for the third one, number of valence is 6. Non-bonding, 1, 2, 3, 4, 5, 6. This is another word for lone pair, I guess. Minus 6, non-bonding. And then how many bonds does oxygen have? Only 1 bond, a single bond. So 1 bond, that's where you get the 1. That becomes 1 bond. So everything is done the same way. I think that it's better, these first two, or that one kind of combines it. It kind of makes sense. An atom can claim all of its lone pair and half of the bonding. Now, if you have a double bond, then remember a double bond would be made of 4 electrons. Carbon-carbon double bond. So if I say, well, this carbon has half of those, then that means 2 of those belong to carbon and 2 of those belong to that carbon. So, or if you have a double bond, it will be 2 bonds. So anyway, okay, I'm getting crazy on that stuff. So here we go. So this oxygen is negative 1. This one is negative 1. And that one's going to also be negative 1. Because they'll all follow the same format. 6 lone pair electrons and 1 shared electron. So 6 valence minus 7 equals negative 1. That's the formal charge. Now for iodine, it will be different. Oh, I didn't mean to erase it so quick. Hope you can remember it now and you can see it if you need to go back. Iodine on the chart has 7 valence electrons. Iodine is 7 right here. Okay? So iodine has 7 valence minus, and it can claim, all right, it only has 2 lone pair electrons. Something on my board right there. That's not a dot. But oh well. It only has 2 lone pair, and then it has 1, 2, 3, 4, 5, 6 that are bonding pairs. Remember, you can have half of each bonding. So 1 of these, and 1 of these. 1, 2, 3 electrons, 4, 5 electrons. So 7 minus 5 electrons equals 2, which is, and it's positive 2. Okay, so iodine is positive 2. I is positive 2. This O negative 1. This O is negative 1. And that O is negative 1. Okay, so now, hopefully, you know how to label the formal charges of each atom. Now, what I'm showing you, when you practice doing this, you'll be able to do it very fast. And it's taking me a while to go through it, but this is an important thing for AP. And we're not done yet. Okay, here we go. Okay, so first thing, one thing that's useful about formal charge, if I add up all the formal charges, negative 1, negative 1, negative 1, plus positive 2, or 2 minus 1 is 0, minus 1. If I add them all up, I get the overall charge on the molecule, or on the polyatomic ion. 2 minus 1 is 0, and minus another 1 is negative 1. It will always match. That's very important to know. If I have a molecule like water, H2O, Well, H is 1 minus 1. So it has a 0 formal charge. This H, 1 valence minus 1, it has a 0 formal charge. Okay? And then O is has 6 minus 1, 2, 3, 4, 5, 6. It's also a 0 formal charge. 1, 2, 3, 4, 5, 6. So it's 0, 0, 0. 0 plus 0 plus 0 is 0, and there's no charge on H2O. But it's interesting. Some molecules, when you do them, you will get like a positive 1, a negative 1. So if a molecule has no charge, you might still have some charges within the molecule, but they'll add up to be 0. Okay. Now, we got that settled. We're not done yet. So why does formal charge help? Well, it turns out analysis shows that iodate is not really 3 single bonds and one lone pair. Okay? What happens is this. The atom in the middle can form some double bonds, especially when you see these oxygens around it. It's almost all the polyatomic ions, they do this. It will form some double bonds in a way to give it a formal charge of 0. Now, here's what happens. The best molecule you could ever, the best Lewis dot diagram you could ever do would be one in which all atoms have a formal charge of 0, like you saw in water. That would be the ideal molecule. Every atom has a formal charge of 0. If it can't be that way, then the next best thing would be, okay, the center atom should have a formal charge of 0, and as many atoms as possible should have 0. So sometimes in this with AP, they'll show you like 5 Lewis dot diagrams, and you look at one of them and say, oh wow, this say you have 5 Lewis dot diagrams, and each one has 5 atoms in it. And you look at it and say, in one of the diagrams, wow, this atom, 0, 0, 0, 0. These all have a 0 charge. But this one has like a negative 1 charge. Okay, well, that could be the best answer. If they all had 0, then that would be the best, ideal. But for a polyatomic ion, something's going to have a charge, at least 1 or 2 things. So what you do is, let me see, I lost my thought for a minute. What you want to do, the best situation, number 1, everybody has a 0 formal charge, okay, for a regular atom, molecule, non-ion. If it's a polyatomic ion, you want as many as possible to have a 0 formal charge. And you want the negative formal charge to always be on the most electronegative element. The most electronegative element in IO3 is oxygen. So that means I want to try to make it so that the oxygens have a 0 formal charge. But if not, if they can't all have 0, then it's okay for a negative charge to be on an oxygen. You don't want it to be on the iodine. Okay, so that is it. Now you might be thinking, how are we going to do this? Watch what I'm going to do, and hopefully it'll kind of make some sense. First, I'm going to take the iodate, and as it is now, I have a single bond, and then I have those 2 there. In fact, I'm going to go on and make a line, because I think it might be easier to figure out this way. So let's just put a single, and a single bond like that. Now what I'm going to do, you know what, maybe I don't want to do that. Well, I'll do that for now. Yeah, I will do that. Okay, now here's what I'm going to do. I'm going to move 2 of the electrons. Well, before I do that, iodine is positive 2. I want to get iodine to be 0 formal charge. And watch how I can do it. First, I'm going to take these 2 electrons off of oxygen. I'll take these 2. And I'm going to put them right here. Okay? Maybe it would be better if I used dots instead. I guess so. Vela. I'm trying to think of the better way to explain it. Okay. So watch what I'm going to do. These 2 electrons on oxygen, I'm going to take them away. I'm going to put them right there. You're like, well, why did you want to do that? Look at what happened. I don't normally stop here, but I'll show you. Iodine, now for one thing, iodine has more than 8 electrons. So when you do formal charge, you will break the octet rule, okay? But now iodine still has 7 valence always, minus the number it can claim now. It can claim these 2, 1, 2, then 3, half of those, 4, half of those, and then 5, 6. it now has a double bond on this side. 7 minus 6 is positive 1. We made the charge go down to a positive 1 now for the iodine. Okay? We also changed the charge of the oxygen, because the oxygen on this side now is going to be 6 valence minus 1, 2, 3, 4, and then half and half, 5, 6. Look at that. The oxygen also became 0. Well, not also, but it became 0. Wow, what a mess here. So I'm going to put the 0 for the oxygen. Can you guys see that with the messiness? Let me put that back. All right, so I'm going to now, I've got the iodine down to positive 1, and I'm going to do one more. It doesn't matter which one you pick. I'll just pick this one. So I'm going to take these 2 electrons and move them here. Now, my formal charge, guess what, is now 0 for the iodine. Because it's 7 minus lone pair 1, 2, then half of these bonding, 3, 4, half of these bonding, 5, 6, and then half of this bond, single bond, 7. 1, 2, 3, 4, 5, 6, 7. 7 minus 7 is 0. Now, one more thing. This oxygen will also be a 0, because 6 minus 6 is 0 for that one. 6 minus 6 is 0. There was something else I wanted to show you right there. I was going to say something and I forgot it. What did I want to point out? Oh, come on. I got to remember this. So the center atom has a 0 charge. Iodine has a 0 formal charge. This oxygen has a 0 formal charge, and this one has a 0 formal charge. The zeros are going to look so messy. That's why I like to use another color for them. I don't know why I didn't do that there. So 0 for the iodine. Maybe I'll put it right in there. 0, 0, 0. Oh, it's like a dot. No, I can't do that. 0, 0, and a 0. Oh, well. I'm doing the best I can. All right, so not every atom will be able to have a 0. If I pulled another one over here, well, then iodine is going to go down to become -1, and that would not be good, even though O would be a 0. So you want your negative charge is going to stay on one of the oxygens. It'll be right there. Now, this particular molecule will not have resonance. Oh, no. It will have resonance. I'm very sorry. It will have resonance. So, because you can put the double bond there, or you can have it either. The single bond could be on this side, or this side. How about that? I'll do it that way. So it does have resonance. So what I would need to do, oh boy. Okay, so I'm almost there. That is one way to draw it. I'm going to use line diagrams now to make this. So I'm going to say it can be iodate. I think it looks a little cleaner like that. Now, you got to make sure that you put your lone pair electrons. Don't ever forget to put those when you're doing a Lewis dot diagram. And the iodine is going to have, is it still going to have 2 lone? Yeah, it's still going to have those 2 lone pair right up there on top. And then, let me just check. Oh, I know what I was going to tell you. I can remember now. You only break the octet rule for the center atom. The iodine in the middle has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, access to 12 electrons. Only the middle atom breaks the octet. But you don't break the octet for the other atoms that are in the molecule. Okay, oxygen still follows the octet. 2, 4, 6, 8. This one has 2, 4, 6, 8. This has access to 2, 4, 6, 8. So only the center atom breaks the rule. So here is one resonance structure. You put a -1 this way. Another resonance structure would be to put the single bond on this side. And the double bond on the bottom. Okay, yeah, got that right. So an arrow between those two. And then another resonance structure would be just to have the single bond on the right. And I'll say that I wouldn't be concerned so much about saying the AP is going to make you draw all 3 resonance structures, but they could have like a multiple choice. They could ask you to pick them, or they could just ask you how many resonance structures will it have. If you looked at this, you ought to be able to figure what will have 3 resonance. Like I'll put like either the single bond will be on the bottom or on the right oxygen or on the left oxygen. Okay, but now what does it mean in reality? In reality, it means this. The iodate ion does not have 2 double bonds and 1 single. Okay, instead, what it has is it has 3 bonds that are equal in strength, but they would be like 1 1/3 bond, if that makes sense. They have 3 bonds. They all have at least a single, but then they share these other 2. Oh, that wouldn't be 1 1/3. It will be a 1 and... Well, let me think about that for a minute. How would that work? You have 1 1 1, and I would have to have that go over to share there. And they would share the other electrons. They would kind of will resonate between them. These other 4 electrons. So what would that be exactly? It's not 1 1/3. It's 1 2/3. It's a 1 2/3 bond. Yeah. Every atom would have a 1 2/3, because 2/3 plus 2/3 plus 2/3 gives you 6/3, which is 2 bonds. 6 divided by 3 is 2. Yeah, it's 2 out of 3. So it has a 1 2/3 bond. Another way to look at that is, what is 2/3? Is it 0.67? Something like that, 0.6667. So it's a 1.67 bond order. I don't know if I've taught that part in this lesson yet, but you can just remember that a single bond, I'll bring it in here, it's going to come up again later. A single bond is called bond order equals 1 for a single bond. For a double bond, the bond order is 2. For a triple, it's 3. Okay? So then you can also have fractional bonds. In the resonance, you'll have a fractional. They all have at least a single, but then you have 2 bonds left over. 2 bonds divided among 3 atoms, that's 2/3. That's a 2/3. 2 divided by 3 is 0.67. So that will be it will be a 1.67 bond order. I can say more about it later. Okay, what craziness is this? Can you believe? Who in the world figured this craziness out? But they want you to know this on the AP. I would say if you can do this, then you're going to be in great shape. But you're going to be in great shape if you can do everything I'm showing you. But most likely, they're just going to ask you a question. You'll see it'll be a little bit easier, but this is a little bit beyond what you might need to do. Now, there's one more really big thing I got to tell you. I'm going to do a couple other ones, or maybe at least one more. Another very big thing to tell you. You only do this, only when the center atom is in period number 3 or greater. Okay, I'm going to hold that up and you can read what I wrote down there. You only do this when the central atom, the center, is in period 3 or greater. So if the center atom is a nitrogen or a carbon or boron, you will not do it with any of this, okay? But if it is anything in period 3, phosphorus, sulfur, chlorine, and higher up and down, okay? The reason for that is because only those atoms have room to do this. You have to have open orbitals, and you have to have open d orbitals in order to break the octet rule. So who has d orbitals? D orbitals don't come until period 3. Remember, 1s, then 2s, 2p, then 3s, 3p, 3d. Even though the 3d orbitals for iodine, not for iodine, but well, let's just say we're picking chlorine. Even though the 3d orbitals for chlorine are completely empty, they can still be used to for bonding orbitals, to make bonding orbitals, and they can still be used as I'm showing you here. So, all right, what I'm trying to tell you is I did iodate. Is there, oh, there's no such thing as a fluorate. But for example, I'll just tell you this, like nitrate. I don't think I did nitrate. You might have to do that on your homework. But for nitrate, I'm not going to do it, but I'm just going to tell you about it. I want to show you something. NO3 -1. Nitrate, or did I do nitrate already in the other video? I don't know. I don't know. Nitrate will have to follow the octet rule. You will not do the formal charge shifting around the electrons. You're not going to do that because nitrogen is in period 2. So any atom in period 2, that's the center atom, the N with the O's around it. You do it. So you go on and you do it the way I showed you, ABC method. So, all right, I'm going to do another one for you here. And I'll just do one more for you. And I might do one more in class. I'm going to do sulfite. So on your homework paper, I'd like you to do all the molecules. Don't do sulfite. I'm doing sulfite. And you don't need to do, let me see, hydrogen phosphite. Is HPO3, is that one on that worksheet? I don't have it with me. You don't need to do hydrogen phosphite though, if you see that one. Okay, but let me do sulfite. Okay, here we go. So I'm going to do it. I'll try and do it much quicker. If you feel good about it, you don't have to watch me do it. Whatever I'll have the video here. You can go on and do the worksheet. Do all those that are on there. I'll have to write it on the lesson which ones to do. But okay, here I go. So first, let's find the valence electrons. Calculate the valence. So we have 1 sulfur, 3 oxygen. Each sulfur has 6 valence electrons. Oxygen, there are 3 of them. Each one has 6. 18. And you know that, of course, because they're all in period 14. No, 18, 17. They're all in period 16, right on the chart. So they have these. And then you have 2 electrons to add to it. So that's 26. So total of 26 valence electrons. Now when I do ABC, A will be, there are no hydrogens, so I'm not gonna worry about putting the hydrogens in here. I'll just, I normally say the ABC method, or A28BC if you want to look at it that way. 2 times H, there are no H's, so 8 times 4, a lot like the one we just did, 32 electrons. B is the valence, which is 26. 32 minus 26 is 6 bonding. So once again, we come into this, all right, with sulfur in the middle, 3 oxygens, and then there are 6 bonding. So in this case, 1, 2, 3, 4, 5, 6. All you would do is have a single for each one. I should have done a different one, I guess. But oh well, no, I'll just do it. In class, we can do another on the video too if you need. Okay, so now make sure everybody has 6. So oxygen has access to 2, 4, 6, 8. Each one has 6 more. Each one needs to have 8. Follow the octet to start off. Sulfur will need a lone pair. This one will get 2, 4, 6, 8. 2, 4, 6, 8. It looks a lot like the one I just had, doesn't it? You know what? It's going to end up being the same thing. I didn't mean to do that, but it's just the charge is -2. Well, but okay. But I'll just show you. I think you ought to be pretty good with it. Now, let's make it so that, let's find out what are the formal charges, and it's going to be the same thing because I can see the same diagram that we've got there. Maybe I should have done phosphite -3, PO3 -3. Is that going to do the same thing though, isn't it? I think they're all going to be. Well, oh well. I'll just head on with it. I tell you what I can do. I think a good idea. I can show you how to make, if you have sulfite, what if I wanted to have an H plus added to it? Remember, H plus has an electron missing. If I added onto that hydrogen sulfite, the charge becomes a -1. Okay, because now you add a +1 to a -2. HSO3. I can show you how to draw that real easy after you do this one. But anyway, so what I'll do, I got SO3. Make sure you know the formal charge of each atom there. So oxygen will be 6 valence minus 1, 2, 3, 4, 5, 5, 6, 7. 6 minus 7, negative 1. It is exactly the same one. I didn't really want to do that. I've already started it, but I don't know if I should just... Yeah, I mean, a lot of them are going to be that way. It would be different for phosphite, I think, wouldn't it be? Phosphite. Well, I guess I better just move on with it. Okay, so then sulfur is going to be... Oh, wait, the sulfur will be different. Okay, yeah, it's going to be a little bit different. Okay, that's... Yay, okay, it's going to be a little different, I think, here, isn't it? Sulfur, at least. Oxygen is going to be 6 valence minus 7, which is negative 1. Each sulfur is 6 minus 1, 2, 3. So 1, 2, then half, half, half. 1, 2, 3, 4, 5. 6 minus 5 is positive 1. Oh, it's not going to be the same. Huh. Okay. Yeah, well, good. I'm glad that I stuck with it and didn't abandon, didn't think, oh, I did this one, because I didn't. It's not the same. Okay, so 6 minus 5. It can claim 1, 2, then half, half, half. 1, 2, 3, 4, 5. All right, so it's positive 1 for the sulfur. All right, so that makes it a little bit easier. So now what's going to happen is it's going to form a double bond with just one of the oxygens only. Okay, so what I'll do is I'll just take, let's just say if I take this one, and I'll just move it over to here. Now, by doing that, from what I showed you earlier, that negative 1 becomes a 0. Okay? And then the sulfur becomes 6 minus 1, 2, then half, half. 3, 4, 5, 6. 6 minus 6, it already becomes a 0 right there. That's all you would do. So for sulfite, now if I want to kind of translate that into to the resonance diagram, it's going to have resonance again. But you have sulfur, a double bond to one oxygen, and you have a single bond to another and another, and then you also have a lone pair right there. And so this one needs to have 1, 2, 3, 4. This one needs 1, 2, 3, 4, 5, 6. And that one needs 6 more as well. So you'd have that form. You'd also have 3 forms, though. How many valence? I can't remember when I calculated the valence, how many there were. Were there 26 valence? Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah. There are 26, 13 pair. I count the pair. 2, 2, 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And 13 times 2 is 26. Yet that will always be true, that those electrons will match. So that will be negative 2, sulfite. You can also draw it with the double bond on this side. And again, I'm not going to... I mean, I might, on one quiz, I might put you through a torture of drawing some of these resonance. I'll give you time. But more than likely, like when the test comes around too, I'll just say, oh, how many resonance forms will it have, or indicate that? Or will it even have resonance? You know, that kind of thing. And then this one, S, put it on that side. Oh, I forgot my lone pair there. Don't forget the lone pair. Okay. And there we are. Okay, so I've shown them all to you there for the sulfite ion. And kind of a weird looking thing, isn't that? So work on those on the paper. I don't know if I'm able to see it on my computer here. I had to wake it up. If it wakes up in time, I'll tell you. Oh yeah, it did woke up. Yay. Well, I'll write this down on the lesson. But you should do, let me see. Wait, do I have it? Yeah, you should be able to do I did sulfite, so you should do sulfate, B, and C, ammonium. You definitely need to do that one if you haven't done that yet. Phosphate, you definitely should do that. Phosphite, actually, on the paper it has hydrogen phosphite. Never mind, don't do phosphite. Don't do phosphite. I'll talk about that later. Do hydroxide, F. And then on the other side, yes, do hydronium. And you can just draw you're going to draw phosphate on letter D. Just show me one form of dihydrogen phosphate on H. One of the, there's more than one, but show me just one of them. And then definitely do chlorate, which is letter I. And then, did you ever do nitrate? You ought to be able to do nitrite. You really ought to be able to do all the others, carbonate and acetate. Acetate I'll have to show you too. But I was going to show you one more thing. Oh, I just remembered. Oh no, how long ago? If I want to turn this, okay, watch how easy this is. If I have sulfite, think about this like even how we did our net ionic equations and stuff. But if ionic formulas. If I have sulfite and I have H plus, okay. When I add, it's plus 1. If I add those together, I get HSO3, and it's no longer -2, it's -1, right? Okay, well, if I wanted to add that on to a polyatomic ion, you pretty much always add the H to an oxygen, and it has to add, it can't add to the double bond oxygen, but one of the other ones. So I'll add it to this right here. I'll just put the H anywhere. I mean, I can go over here and put it on the end. I'll put it right there. Now it's -1. That's HSO3, and the H will join onto it to one of the O's. So the H plus just had no electrons. It just came and just joined onto a lone pair on one of the oxygens. It has 3 lone pairs. That's how you draw HSO3 -1. It's actually called bisulfite ion. HSO3 is bisulfite ion or hydrogen sulfite. We didn't have to ever memorize that one. Now, of course, this has resonance, because you could also then have the double bond down there. But you only have 2 resonance, actually. It would just have this, and then it would have the double bond there, and of course move the electrons over here. Because that traps, these electrons cannot be part of resonance once they have the H over here. But these 2 can. So it has 1, 2. And, okay, and if you had to do H2SO3, it would have no charge now. If I add 2 of those H plus onto that, then you just put the other H right here. And now you no longer have brackets around it because it's HSO3. HSO3. H2SO3. I'm sorry, H2SO3. Craziness. But I'm telling you that this is more than you probably need to know. All right, I'll see you guys.